Okay, so let's start our afternoon session. Now we'll have two talks, one talk today and one talk tomorrow by Pedro de Holanda from University of Campinas. Today is non-standard neutrinos, and then tomorrow, neutrinos and astrophysics.
Okay, thank you. Thank you, Martin, for inviting me. It's a pleasure always to be here. So, as he said, it's a two-part talk. Today I will talk a little bit about non-standard neutrinos, assuming some of the things that André already told you. So I'll kind of start where he left today. Okay, so non-standard neutrinos is a very generic term to anything that is not the standard 3x3 neutrino oscillation, mass mixing neutrino oscillation. So I will talk about non-standard interactions, which is probably the main thing people talk about when they are talking about non-standard neutrinos. A little bit about the coherence, magnetic moment, and just mention other kinds of things that we can do with non-standard phenomenology. And a little bit about non-standardness in cosmology. Not a lot about that, but it's something that we have to think about when we talk about neutrinos also. Okay, so starting with non-standard interactions, the one simple way to parameterize the non-standard interaction, any interaction which is not on standard model, would be through dimension 6 operators and just adding some new interaction with some new mediators that have this kind of very generic form, where you just mimic the normal interaction with some new bosons. So we have the neutrinos here, and if we have a charged current interaction, we have the neutrino with its lepton and some other fermions here. But this kind of interaction is very constrained by cross sections, because it involves normally it involves the charged lepton, which is very easy to make experiments, so I will not focus much on the charged current non-standard interactions, but instead I will talk more about the neutral current interactions, where on the interaction vectors involve only neutrinos here and the charged fermions here. And these kind of interactions are weakly constrained by scattering cross sections. So we can look for the strongest constraints on this term in neutrino oscillation experiments. Okay, so this will be the focus of the non-standard interactions, and this is the kind of thing that we will analyze. We have the usual Lagrangian, very similar to the one that gives us the usual interaction, forward scattering interaction with electrons, that probably André told you about when he was talking about solar neutrinos. It's the main ingredient, one of the main ingredients of solar neutrino phenomenology is the interactions of the neutrinos with the electrons on the sun. So this is very similar. You have the same kind of mechanism. So you could put here the Fermi constant, which is not the constant involved in these new interactions, but then you correct it with a dimensional parameter, epsilon, which will basically compare these new interactions, the strength of these new interactions, with the usual interactions with matter. So, just coming back, these interactions can depend on several things. So each of these things, we collect one index here. So alpha and beta are the flavor of the neutrinos. The P for parity and F for the fermion involved in these interactions. So it's a very generic way to proceed, but this is too generic. So we start to make some assumptions so we don't have too many parameters to test on neutrino oscillations. So the first assumption, which is a very reasonable assumption that again is already present on the standard interactions, is that only vector interactions contribute to the neutrino oscillation phenomena. So the parity here, the sum on the parity, it's performed, we can define this epsilon f as the sum of the left and the right components of these new interactions. Again, nothing new, just copying what happens in the standard interactions with matter. So we have one less sum on these various indexes. Besides, the first one is very straightforward assumption. The second one, not so, but we can make a reasonable assumption that the neutrino flavor structure is independent from the fermion involved. So we can break the sum on the index of the fermion with the neutrino flavor. So now we have two different sums. And then, with this, and also assuming that we are talking about ordinary matter, we can talk only about quarks, U quarks and D quarks. So we can do one more simplification, which is talk about some different compositions of these new interactions with U quarks or D quarks, and put everything in a much simpler form, which is one parameter that depends on alpha and beta, which are the neutrino flavors, and everything else is hidden here on these different weights on the D quark and U quark new interactions. Also, we have electrons, which are we know that electrons, of course, are on the ordinary matter, but then we are also talking about neutral matter, so we can always hide the new interactions with electrons with some reparametrization of the U and D quarks. So basically, it's enough to, yes. This alpha beta and beta comes here from the flavor of the neutrinos. In a most generic way, you can have these interactions can depend in a non-trivial way on the neutrino flavors and the kind of fermion that you are interacting. So when we break this, we can break this index this way. We say that the new interactions that acts on the neutrino flavor can be parameterized by one epsilon, and then the lepton here can be disassociated with this interaction, with this parameter. Okay. It's just it will get simpler at the end because, well, now we have this kind of parametrization, and then we can put everything together in several different ways. This one is one particular way that Esteban et al. In this very recent article proposed to just put all the numbers together in a very simple and straightforward way to see these new interactions, which will be to parameterize the strength of the new interactions, the neutrino new interactions with U quarks, and the strength of the neutrino new interactions with D quarks in a very simple way. It looks like a mixing matrix, but a little bit different, just to have this kind of property that we can think about the interaction with the quarks, looking at this new parameter at eta. When this new parameter eta is 0.5, we only have new interactions with U quarks. When this new parameter is the tangent of this new parameter is 2, we only have interactions with D quarks. It's just a choice of parameters, nothing physical here. But it's easy to put everything together in only one parameter. And if we do everything this way, we could finally arrive at the Hamiltonian, the modified Hamiltonian, because of these new interactions. Usually, we start talking about new interactions, new non-standard interactions on the neutrino sector with this Hamiltonian. We just say that, look, there are several different ways to interact with matter besides the usual interactions. But it's important to stress that there are some assumptions on this structure. We talk about parity, left, right, this assumption of independence of fermion and flavor, neutrino flavors, so, the kind of composition that these neutrinos are filling. So, but anyway, if you take all these assumptions, we can simplify our Hamiltonian and include new terms on this Hamiltonian and study how these new terms will affect neutrino oscillation. So here we have the standard interaction already present, as I said, on solar neutrinos, very important on solar neutrinos, very important on the determination of mass hierarchy, as Andre pointed out this morning. And then we have also these new kind of interactions. One thing that we should take into account, the eta dependence is here. It's suppressed just not to put much to carry the notation too much. But it also has some x dependence on these terms because it depends, of course. There's a x dependence. X is the distance traveled by the neutrino. If you are traveling through a varying density, of course, all these parameters are not constant. They will vary according to the neutrino evolution. But anyway, with this Hamiltonian, we can start to check if including this new kind of, sorry. Jesus, what's that? Sorry. We can start to test which kind of neutrino experiments, oscillation neutrino experiments, are most sensitive to which kind of parameters. There's some steps to do that because this is a 3x3 matrix and we know that it's a lot of new parameters and it's usually easy to reduce this 3x3 system into a 2x2 system and then talk about effective couplings, which will be a mixture of these new parameters with the mixing angles. It involves some analytical procedures to do that, but it's not very enlightening, so I will just assure you that I will talk about 2x2 evolution equations, but all these parameters we have to always check which kind of parameters we are testing when we go from different neutrino experiments. Okay, so talking about solar neutrinos. This is the usual probability of the solar neutrino survival probability. I didn't check how much did you talk about that, but here we have the usual vacuum oscillation without the average terms, because we are talking about solar neutrinos. They oscillate a lot between the solar and the sun. So this is just the amplitude of the oscillation. And here we have the MSW effect. So the transition between the vacuum oscillation and the MSW resonance with an energy around some MeVs. And what happens when you include non-standard interactions, for instance, is to change where this kind of transition happens, because this transition is very dependent on the interaction with the matter in the sun. Here we have too low, the energy is higher, so that the oscillation term, delta m squared over 4e, is lower. So we have a stronger interaction with the matter. Here we have a lower interaction. So if these new interactions enhance the interactions with the matter, we will move this transition to the left. If it decreases the interaction, we will move this transition to the right. And the solar neutrinos experiments see these transitions. So in principle, it can put constraints, look for this signature on the data, and put constraints on the new parameters. Okay, so also another thing that is happening in solar neutrino is the regeneration effect. The neutrinos that come to the detector through the night interact with the matter of the Earth, and the electron neutrino flux regenerates, and you expect more electron neutrinos during the night than during the day. And again, if we change, and Super Kamiokande, SNO, they are seeing this effect, is a more than 3 sigma effect. In fact, the electron neutrino is stronger during the night than the day. So we know this interaction is happening with the Earth matter. So again, if we put new interactions, we must be careful not to enhance too much or vanish out this kind of interactions with the usual interaction with matter. So these are the 2 observables that we can look for on neutrinos, on the solar neutrino analysis and solar neutrino phenomenology with new interactions. Okay, and the current picture of solar neutrinos is we have some allowed regions for the mixing parameters, theta 1, 2 and delta m squared 2, 1. I don't think I should be too detailed about that, right? And we have only solar neutrino experiments, we have this kind of allowed regions for these parameters. The best fit point for the mixing around the sine squared of theta 1, 2 around 0.35, and a low delta m squared around almost 6 times 10 to minus 5 electron volts squared. Also, we have Kamland results, which confirm this solution to the solar neutrino problem, but with higher delta m squared. Everything is compatible between inside the 1 to sigma regions, but they not coincide completely. The best fit points of solar neutrino analysis and Kamland doesn't coincide. So people started talking about some tension between the solar neutrino data and Kamland's data. It's a tension, is not exactly an indication of anything new, but it's something that we can try to think about when we talk about non-standard neutrino interactions. And also, well, this can mean nothing, can mean statistical fluctuation. If it's not a statistical fluctuation, it can be solved by new physics on Kamland, or it can be solved by new physics that on solar neutrinos. The new standard neutrino interactions, in principle, can change the behavior of the solar neutrino survival probability, and push this. If we push these things to higher delta m squared, it will be achievable by including some non-standard interactions that kind of cancel the usual interaction. You put some while the normal interactions make this transition happen. That here on this region, if we put some new interactions with the wrong signal, we can put this transition on the lower energy, and this would be the consequence of this would be to get a better adjustment with the data in a higher delta m squared. So in principle, this tension can be addressed with new interactions. 1.8 sigma or something like that, but yeah, it's a small tension. You can see that the 1 sigma, I think this is not 1 sigma, I think this one is 95% confidence level, 90, okay. So yeah, it's a tension, and that's why I always put this kind of thing when I talk about this tension. So you are not supposed to, everybody is familiar with monsters, I suppose, right? You are not supposed to name it, but once you name it, you start getting attached to it. So people started talking about tension, and when we start talking about tension, we try to solve it. So, and the new interactions can solve this tension, in principle, by changing the strength of the interaction, neutrino interaction with the solar matter. Okay. So this, the Miranda and the et al. In this paper on, in 2006 made this analysis, and they found what they had to found. Some specific negative values of this diagonal parameter, which would be the parameter that adds or subtracts the usual interactions. You can see a best fit on lower, on a best fit on non-zero new interactions. Again, let's stress out that the difference is very small, but it's present, and well, I'll talk about more about the significance of these results in some seconds. And again, as I said, we write, when we present these results, we always write it in two neutrino formalism. But these parameters are those 3x3 parameters rotated to a 2x2 system. So here we have some effective new parameters that depends also on the mixing angles of the neutrinos. Okay. Okay, so we have negative values here that would enhance the matter effects and allow the best fit point on solar neutrinos to raise to higher values of delta m squared and increase the compatibility with cumulant. There are other interesting features of this kind of game. One is that if we increase the value of the amount of new interactions that we have, we can have some new kind of solution to the solar neutrino problem with an inverted hierarchy, and here not that inverted hierarchy that André was talking about, is an inverted hierarchy between the first and the second family. We usually don't present it as an inverted hierarchy because we can solve that going to mixing angles higher than 45 degrees. So what happens is that if we extend the parameter space to, again, higher than 45 degrees angle, we can have a negative cosine of 2 theta. So on the evolution equation, we flip the sign of the usual parameters, and then if we correct, then there is no, without new standard interactions, there is no resonance inside the sun. But then when we include the non-standard interactions, we recover the resonance, and we have a very similar allowed regions that they call LMAD, D from dark, here on this parameter space. Yes. Sorry, this is the same as here. I didn't put it, sorry. It's the delta m squared. So here we have delta m squared and the mixing angle. The usual two parameters, two neutrino oscillation parameters. And then we have this new region happens here for a reasonably high value of new interactions. Remember that this epsilon is the comparison between new interaction and usual standard model interactions. So to get this solution, we should have almost equally strong new interactions on neutrino sector. But anyway, it's here, it's allowed, and it gives us a new oscillation, new region on oscillation space. This is a kind of old plot. They still have some new regions, but now we are with these two lefts. Okay. Okay. Another interesting feature of this mechanism is that the sun has some structure, some matter structure, where you have more helium at the center of the sun, more hydrogen at the outside of the sun. So it's, if you choose, fine-tune the amount of new interactions with the d quarks and with the u quarks, it changes in a very specific way during the evolution inside the sun. So what gives us that interaction with d and u quarks is that new parameter ether that I showed before. And what it's in one specific region on the value of this parameter, you can cancel any effects of new interaction inside the sun with a very high value of these new interactions. But because of this composition of the sun, you cancel out these effects on the sun, and these effects show up on Earth, where you have a different kind of matter composition. So at this specific point, you could have the other kind of solution to the tension between Cumberland and solar neutrinos. You could have almost no effect on sun and a very large effect of new interaction on Cumberland, the Earth experiment. So lowering the delta M squared on Cumberland and achieving a better concordance with solar neutrinos. And this is what is pictured here. You have the standard parameter space again. I am copying this from the paper, so I lost the axis. Here is the mixing angle. Here is the delta M squared. But you can have again for one specific parameter. One specific choice of value for this parameter that gives us the amount of the comparison between the interaction with d quarks and u quarks. You can cancel out all the effects of new interactions in the sun and have a very large effect on Cumberland. So you can lower the best fit point on delta M squared on Cumberland. Okay. However, again, this is only solar neutrinos. Now we have to take these values of the epsilons that we are obtaining and check out how they influence all the other neutrino data. Atmospheric, long baseline, reactor experiments. So if we do that with atmospheric and long baseline neutrino data, what we get, well, first of all, it's a different set of parameters, because now we have, again, we will reduce that 3x3 matrix to a 2x2 matrix, but the reduction is different if you are going to solar neutrinos or atmospheric neutrinos. Atmospheric neutrinos, mainly you have the 2-3 system, muon and tau neutrinos. On solar neutrinos you have the 1-2 system. So this kind of new interactions parameter, it's a different composition of those initial parameters on the 3x3 matrix. But anyway, we are testing the same phenomena. So another difference is that the Earth is, we can think about the Earth as a constant density, kind of constant density, with a constant composition of d quarks and u quarks. So it's a much simpler environment to implement new standard interactions. And we can translate this kind of interaction with u quarks and d quarks into interaction with protons and neutrons, just to make it easier to analyze the conclusions. So we have interaction with protons, interactions with neutrons, and resulting in an effective coupling with the Earth matter felt by the neutrinos. Okay, again, we have to take into account, we have to reduce that 3x3 matrix into a more easy way to deal with the probabilities. There are several ways to do that. They propose, the same group proposed to use a very similar structure that we have on mixing, the mixing matrix, the usual mixing matrix. some angles that rotate the new interactions into a diagonal state where you have these new interactions. What affects neutrino oscillations? What affects atmospheric neutrino oscillations are basically two parameters, which again is composed by a lot of mixing angles and some different combination of those new parameters. Okay. And what they obtain when they compare this, when they try to fit atmospheric and long baseline neutrino oscillations with these new interactions, they have this kind of the allowed regions are everything in green. Okay, so you have, let's talk about the epsilon. We have the epsilon, this combination of epsilons, which I didn't write because it doesn't give us much more information. It's constraints between -0.1 and 0.1 with some space for very strong cancellations and very large epsilons, values of epsilons. And this is what we obtain for atmospheric and long baseline data. If we include solar neutrinos, we can put everything together here on these other islands of allowed regions. And again, you can see that since the solar neutrino data favor non-zero non-standard interactions, your islands of allowed regions are does not include in 3 sigma the absence of new interactions. So we have these islands of possibilities where which is compatible with all solar, atmospheric, and neutrino data. Okay. One interesting thing some interesting things to notice. The best fit point is not on 0. Also, of course, we have to put some grain of salt there because we still doesn't have a strong indication that these new interactions are there. But anyway, the best fit point is getting out of no new interactions. The other interesting thing is that the new allowed region that we found out on solar neutrinos with very strong new interactions and higher than 45 degrees mixing angle survives to this check with other experiments. So when we include atmospheric neutrino data and long baseline neutrino data, we still have this kind of new region with, as I said, a very strong new interactions. Okay, so what I just said, best fit point for non-zero non-standard interaction, and the non-standard interaction is working as the leading mechanism in large mixing angle on the dark sector, which is how we call the higher than 45 degrees. Okay, so this is the everything together picture in the new parameters. Then we can now look at the everything together picture on usual standard neutrino oscillation parameters. In solar sector, we can see that this is the allowed region with only solar plus chemland. As I pointed out, it enlarges the possibilities on delta M squared. But when we include the atmospheric and long baseline, we again shrink it down around the usual oscillation region. So if we look at the value of the delta M squared is with or without new interactions, we are always between 7 and 8 roughly times 10 to minus 5 electron volts squared. As I said, the dark solution to solar neutrino is still there with only solar plus chemland surviving when we include atmospheric plus long baseline. And on the atmospheric delta m squared, we also have a very strong determination of the oscillation parameters. We have these allowed regions with everything included, not changing much from the usual oscillation parameter solution, excluding ice cube, which is the I don't know if you already talked about ice cube, the atmospheric neutrinos in ice cube, excluding the atmospheric neutrinos detected by ice cube, or excluding solar and Cameland neutrinos, you always get more or less the same picture, and everything together we have a very similar allowed region in comparison with the no new interactions regions. So what we can conclude by that is that we have, even if we include new interactions, this doesn't change much the capacity to pinpoint the values of the usual oscillation parameters. Delta m squared on atmospheric and solar must be around 2.3 10 to minus 3 and 8 10 to minus 5 electron volt squared. The mixing angles must be close to maximum on atmospheric, close to that value of 0.35 on solar neutrinos, and including new interactions doesn't change that, with one exception, which is the possibility to go to the large mixing angle dark region of these parameters. This will be completely different, the same values for delta m squared, but a complete different region for the mixing angle. Yes. Yes, always, let me check here. Yes, it's sine squared of theta. It's the inverted hierarchy. So as yes, of course, yeah. And here they put it mu because it's an effective, it's not the 2-3, but anyway, let's think about the 2-3, and this is me3 squared minus me2 squared. So if you have inverted hierarchy, you have a negative value for this parameter. So it's just the inverted hierarchy that André started talking about on today's seminar. And so, okay, we still have this possible high this important region where the interactions are the leading mechanism on neutrino flavor neutrino conversion. But besides, if we forget about that for a minute, we have this good determination of usual parameters. So we can, for instance, plan our future experiments kind of knowing that the predictions for those parameters are robust. But at the end, the NSI, when we put together solar plus Cameland and atmospheric and long baseline, it doesn't help the range of parameters that help it to resolve the tension between solar and Cameland disappear. It's excluded by atmospheric and long baseline, and we still are left with that tension, which should be resolved in some, or not, in some other way. So it's something that's still there, that if we want to address that tension with new physics, it still has room for that. Okay. With this panorama, where do you go from now? One, to new experiments, of course, and one possibility is to study how, for instance, Dune will have what's the sensitivity of Dune to these new experiments. This instead of talking about that, I included as some exercise that you can think about during the exercise session, which would be the following. We can look for the Dune's precision in establishing the values of delta m squared, which is any paper, Dune paper will tell you that. and we can analyze the effects of new epsilons on new interactions on the determination of delta m squared and theta 2, 3. And kind of estimate the limits obtainable on Dune, so these values doesn't change much. Okay, I left this as an exercise, and then we can talk more about that. Okay, going for another possible mechanisms. One non-standard mechanism on neutrino section that I worked a little bit on is on dissipations. Again, we have the standard oscillation paradigm and some new effects. And this, when we talk about the dissipation, we have to go beyond quantum mechanics. So the Liouville equation dictates what happens when we have the usual quantum mechanics. This is exactly equivalent to have this Hamiltonian evolution of neutrinos, of flavoneutrinos. It's just written in density operators, nothing that you didn't do in any quantum mechanics course. So what we do here is to add something new, which is non-standard, and not only non-standard, it's not quantum mechanical. So we add it here as a little bit more technical, as a symmetric operator in this space, on this density matrix space. And we can try to analyze what are the effects of this new non-quantum mechanics term on the neutrino oscillations. Now we have two ways, basically. We have several ways, but two main ideas that we have to think about when implementing this kind of new physics. One is if we have no energy exchange between some environment and neutrinos. We usually think that some kind of interaction with some environment which leads to decoherence, this can be accomplished with energy exchange with the environment or without any energy exchange. This will give kind of different effects on neutrino oscillation, so we can split this phenomenon of dissipation into decoherence or relaxation. It's kind of a terminology, but it's the way we speak about the different ways to implement dissipation on neutrino oscillation. Decoherence, we usually talk about decoherence when there's no energy exchange between the environment and neutrinos. So the energy carried by neutrino sector remains constant. And if we can have energy exchange, then we call this relaxation. Okay. So the decoherence, this I will not go into the details of that, but this is the way we implement the decoherence. We have to take into account some for instance, we have to impose energy conservation by making these new operators commute with the Hamiltonian. We have to, we can impose that the entropy always increases in the neutrino sector. This will make another constraints on these new operators. And if we do all these considerations, we can write these new operators as proportional to the third Pauli matrix. And in this simplest possible case, two families, only decoherence, no relaxation, we can have, we arrive at this kind of two neutrino probability. The gamma here is where all these new effects are included, and we have the usual oscillation probability when gamma is equal to 0. So we have the mixing angle here and 1 minus cosine of delta m squared over 2ex, which is the usual oscillation. And what this new parameter does is to reduce the coherence term on the neutrino oscillation. That's why we call decoherence. So it kills the oscillation term faster. And so if the experiments that can probe this kind of effects are the experiments that sees the oscillation pattern more clearly. Okay. So it suppresses the interference terms in neutrino conversion, and since we are invoking energy conservation, it does not induce mass eigenstates conversion. Nu1 is always Nu1, Nu2 is always Nu2. What we are doing is killing the coherence between Nu1 and Nu2, the two mass eigenstates, neutrino mass eigenstates, that creates the coherence and the neutrino oscillations. So this is the kind of effect. As I said, the experiments that are sensitive to this kind of effects are the experiments that sees the oscillation pattern. So Cumberland is one of these experiments. So if we plot Cumberland results as a constant value of a distance over the energy, you see by the data clearly the oscillation pattern, and we can we can plot over the data the usual solution to Cumberland, which is the usual oscillation here in black, and then we can include some decoherence effects, and we can see that the effect of the decoherence is killing the oscillation pattern. So when we have a higher probability, it comes lower. When you have a low probability, it comes higher. It tries to bring everything to the average value. And of course, Cumberland doesn't want that, so we can use Cumberland to put some limits on this kind of effects. We have very small improvements on fit to data, nothing that worth mention. But the main thing that we can do with this analysis puts some stringent limits on large decoherence effects. So as far as we can tell, there's no clear indications that we need this kind of mechanism acting on neutrino sector, so we can put some limits on the decoherence. If we include the relaxation, then we have more parameters. But then some again, we have some new effects. But one thing that we can stress is that since now we have possible energy exchange between environment and neutrino, what the tendency when we include relaxation is to have equipartition between neutrino flavors. I will come back to this tomorrow when we talk about astrophysics, and because in astrophysics all the sources are very, very distant, so it's important to know what's the flavor composition of neutrinos when they arrive at Earth, when they travel a lot. The decoherence changes a lot how this flavor composition of the neutrino flux arrives at Earth. And then we can use this idea to put some stringent limits, and the best way to do this is to not to look at the oscillation pattern, but to look for neutrinos that travels a very large distance. So this equipartition takes place, and we can limit these new effects, comparing, looking if the signal we get is compatible with equipartition or not. Again, I will talk more about that when on the next tomorrow when we talk about astrophysical source of neutrinos. Other possible scenarios. One thing that one possible extension of the standard model includes a non-zero value of magnetic moment. Actually, let me correct this. The standard model predicts a non-zero magnetic moment to the neutrino, but it's too small to have any effects on anything, any experiments on neutrinos that we saw on this school. But there are a lot of non-standard models that can increase by several orders of magnitude the value of the magnetic moment. And the effect on this large magnetic moment on neutrinos will be changing the cross-section, because if we have this magnetic moments, the differential cross-section, electromagnetic cross-section of the neutrinos will change by a factor proportional to the magnetic moment squared, or you can change the oscillation pattern, because now a magnetic moment, a transition magnetic moment, can convert a neutrino into an antineutrino. If, in particular, if we are talking about Majorana neutrinos, again, I'm not getting into the details here, but if we're talking about Majorana neutrinos, you can convert an electron neutrino in muon antineutrino through a transition magnetic moment. And then, for instance, we can go to the sun, again, to the solar neutrino experiments, and look for any antineutrinos on the solar flux, neutrino solar flux. And what we one thing that there are two things that we can study with that. One would be probe the magnetic fields in astrophysical objects, and actually the strongest bounds we have on the neutrino magnetic moments is from the cooling of stars through neutrinos, and if we include magnetic moments, the interaction with the neutrinos with the magnetic field on these stars will spoil the model we have for those stars, and it's the strongest limit that we have on the magnetic moment is coming from the analysis of these astrophysical objects. But we could also constrain by looking for antineutrinos coming from the sun. The solar neutrino experiments are not very sensitive to the difference between anti-muon neutrinos or muon neutrinos, anti-tau neutrinos or tau neutrinos. But electron antineutrinos are very constrained because they are very talking about neutrinos, but very easy to detect, and we have a very strong limit on the amounts of electron antineutrinos coming from the sun. So what could happen here is the electron neutrino that is created on the sun converts to muon antineutrino, but we know that this muon antineutrino oscillates, so it oscillates into electron antineutrino. So we cannot allow this mechanism to be present on solar neutrino flux, and if we look for the data, we can exclude a large portion of the magnetic moment on the value of the magnetic moment. This is a recent work where we excluded this region here, looking for modifications, production of electron antineutrinos in solar neutrino flux, and this other region is excluded by Borexino, which is a solar neutrino experiment, but through analysis of the cross-section. So this region excluded by cross-section, this region excluded by production of electron antineutrinos, and then we have some allowed regions, magnetic moments, a combination. Again, we always talk about combination of different magnetic moments with different values of the mixing angles, but anyway, we have this kind of allowed regions lower than around 10 to minus 11 magneton of Bohr magneton for the values of these new magnetic moments. Okay, as I said, a lot of different things that we can talk about non-standard neutrino physics, neutrino decay, mass-varying neutrinos, Lorentz violation of equivalence principle, stochastic neutrinos, and there's no generic way to address this issue, because every one of these mechanism has a distinct signature, a distinct effect on the neutrino oscillation probabilities. So you have to go one by one, checking what are the limits on each one of these new phenomena. And so far, standard oscillation mechanisms is robust, and only limits are obtained on non-standard physics, with some remembering that we have that large mixing angle, dark solution to the solar neutrino problem. That's the only place where we can have a very strong and necessary new physics happening. And no clear signature of necessity for non-standard mechanism so far. And here we have some observation because, of course, we say that, we can say that because the usual 3 neutrino oscillation paradigm is robust, but we know also that there are a lot of things to talk about when we go out of this 3 neutrino paradigm, which is the reactor anomaly, the sterile neutrinos that the Orlando told you about, the mini boon, LSNG new data, the tension on Cumberland and solar neutrinos. So these are the places where the new physics could be around. But anyway, it's too soon to say. For now, it's safer to say that we only established a lot of limits on any new model involving neutrinos. I will say a little bit more about sterile neutrinos because, well, this is something that Orlando must have told you yesterday, that we have yes, it's a strong indication of something off on mini-boon LSNG data, which can be interpreted as a fourth neutrino oscillation involving a fourth neutrino, a sterile neutrino, because we can only have 3 active neutrinos. And the parameters that explain the mini-boon LSNG results are delta m squared around 1 electron volt squared, and sine squared 2 theta around 10 to minus 1. So, okay, we have this picture for the accelerator neutrinos, but now we have to go to cosmology and ask them if this is okay. What cosmology has to say about this new fourth family, because we know they don't like, cosmology doesn't like new particles being created if they cannot include it in the standard cosmological picture. And in fact, a new neutrino with that parameters would count as radiation, so it will affect a lot of the cosmological observables. For instance, it will change the time of equality between matter and radiation. It will change the number of effective degrees of freedom during BBN, the Big Bang nucleosynthesis. So it's not easy to accommodate a fourth neutrino family, especially with such large mixing angle with cosmology. But okay, how should we? The kind of computations that we should do to accommodate that would be, again, go back to the flavor. This is more or less the kind of thing that we should compute to have those production of sterile neutrinos that we just saw on Andres' talk, and we include then this new neutrino on this new sterile neutrino, but it's not so straightforward to include it. So there are a lot of still uncertainties on how this sterile neutrino will be produced. Here we have the usual oscillation pattern, the new interactions, and up to here it's everything on density matrix formalism. Up to here is exactly the usual oscillation scenario. Okay, so it's everything that we saw, the oscillation of the 2 neutrino, 3 neutrino oscillation, evolution equation. It can be written in a different way with density matrix, and this is what we get. Okay, but when we go to cosmology, things are kind of different in the early universe, because when we calculate the neutrino oscillation probabilities on Earth, we know that we don't have antimatter, for instance, on Earth. In early universe, we have electron neutrinos as well as positrons. Sorry, we have electrons as well as positrons. So we have to include also the positrons. Also, these electron and positrons, if you go again to early universe, they are almost the same number, because we have a very small baryon, asymmetry between matter and antimatter. So basically, when we include the electrons and positrons, this term vanish. So we have to go to the second order on this. I don't know how much Andre stressed that this kind of inclusion is it's a first order approximation, which is very, very, very good for neutrinos oscillating on Earth. But when we go to cosmology, because we have this cancellation, it's not so good, so we have to go to second order. And also, we have to include some neutrino-neutrino interactions, because also, again, we doesn't have to bother about that on solar neutrinos, atmospheric long baseline neutrinos, because the neutrinos density are too small. But if you go to early universe, the neutrino densities are very large, so you have to include the neutrino-neutrino interaction. Everything here is standard physics. We just didn't include it before because it was not necessary. And now we have here the evolution of the density operation, and here the density operators here inside the neutrino-neutrino interaction. And this brings us a very, very serious complication, because everything now becomes non-linear. The things that are changing here are inside integrals here. So to solve this analytically is very difficult. You only have some hints, analytical hints, and you have to do it numerically. And even to solve it numerically, it's not very, very easy, because it's very time consuming. Then you have to make a lot of assumptions and simplifications to get some results out of that. But anyway, if we take everything into consideration, it's these numbers here is just to remind you that things are complicated when you go to early universe into cosmology. But then you have this kind of production of neutrinos. It's parameterized as a new degree of freedom, going to 0 if no neutrinos are produced, 1 if the neutrinos, this fourth neutrino family thermalize with the other particles. So we have the best fit points of mini-boon and LSNG in a region where it is practically thermally produced in early universe. So it accounts as a whole new family of neutrinos when we do cosmology. And this spoils everything that we know about cosmology, structure formation, CMB. Cosmology doesn't want that at all. It limits the new family, new light family of neutrinos to 0.4 or 0.5 degrees of an effective number of 0.5 to the neutrino population. So this is a normal hierarchy, inverted hierarchy. So in both scenarios, you cannot have the sterile neutrinos that are solving the mini-boon LSNG data. Okay. Okay. So what do we do to compatibilize cosmology and sterile neutrinos? Well, this is, as I said, we come with non-standard sterile neutrinos, right? What did you say? So, sterile neutrinos is already standard. Everybody understands everything. Sterile neutrinos is standard neutrino physics. So now we have to put something else above the usual sterile neutrino mechanism to solve the LSNG mini-boon problem, and does not spoil, and we cannot spoil the cosmological data. There are several ways to do that. How many times do I have? None, right? So there are several ways to do that. I will just point out how some mechanisms that are possible. One is to have a large lepton asymmetry. But you cannot have a large lepton asymmetry. I learned that the asymmetry between matter and antimatter should be low, around 10 to minus 10. But this is on baryon sector. On lepton sector, things are more easy to accommodate, so in principle we can have up to 10 to minus 2 lepton asymmetry without spoiling everything else that we know about cosmology. And if we include this lepton asymmetry, if we and go back to the evolution of neutrino and the sterile neutrino production, we can include it in a way that cancel the the sterile neutrino production. So in principle, invoking a large lepton asymmetry, but how this lepton asymmetry is produced, I don't know, let's talk about it later. But if we can produce a large lepton asymmetry, then we can push this, we can suppress the sterile neutrino production, and then we have a very low sterile neutrino production, giving around 0.1 more on number of degrees of freedom of relativistic species with a lepton asymmetry of 10 to minus 2, both in normal hierarchy and on inverted hierarchy. So there are ways to accommodate this fourth neutrino with cosmology, but as I said, we have to put something else beyond the sterile neutrino. There are another ways to do that. I will not enter into the details here. There are secret, for instance, secret interactions. We can have neutrino-neutrino interactions that can also suppress the production of the sterile neutrino in early universe. But then this can happen. Solve the neutrino, the cosmology problem, the problem of this fourth family on cosmology. But then, when we come back to Earth-based neutrino experiments, these secret interactions can have a non-negligible effect on neutrino oscillations. So, for instance, for this particular mechanism, you include this new secret interaction, go back to, for instance, minus, and you see that the effect on minus that could, correct me if I'm saying something wrong, the effect of minus would of this new physics would spoil the accordance, the adjustment with the minus data. So it's not a very trivial task to include new physics on sterile neutrino sector to accommodate both cosmology and Earth-based neutrino experiments, but it's something that we must do. Anything, this kind of data, this kind of new phenomenon has to be always has to look on cosmology on the large scale and on the neutrino experiments on our small scale here. We cannot treat this new physics independently anymore, right? I also pointed out this article just to say that things are happening on this field with some interesting results. For instance, on this article, the authors stress that it could be an indication of signs of new hidden interaction in the dark sector, because you can solve some of problems. You can have a sterile neutrino, you can solve some problems on cosmology, and still have a good agreement with oscillation neutrino experiments. So things are happening. And just to conclude, let me put everything. One thing that I try to emphasize on these slides is that there are no one thing called non-standard neutrino phenomenology, because every mechanism non-standard mechanism has very distinct implications on the neutrino experiments or in cosmology. So it's a very broad field that we cannot accommodate in only one title. I did that to give this talk, but you shouldn't do it. Okay. And the other thing that we can learn is that we have to take all data into account. For instance, we saw that to constrain the non-standard interactions, it's not sufficient to talk about solar and cumulant neutrino. It's not sufficient to talk about atmospheric and long baseline oscillation experiments. We have to take everything into account. The 3x3, it's a lot of work, but if you take everything into account, the allowed parameter regions that you come to, that you find in one experiments are not allowed in another, and when you have everything together, you can have very stringent values for those new interactions. And of course, when we talk about that, we must include cosmology. Okay. And for now, we only have limits and hints, no clear indication for the presence of non-standard physics. But that's the way it goes. We shouldn't be too worried about that. And this is a dark matter and neutrino school, so yes, we don't have any good indication until we have that indication. So we just keep looking. So this is kind of the rules of the game. If you bet that you will not see anything new in the next round of experiments, I'm sure you will win. But in 10 experiments, eventually, in 20, 30 rounds of experiments, eventually something new will come up, and then we are prepared to deal with this new data, these new indications for new physics, and hopefully accommodate, extend the standard model to include new effects. So that's it.
So now we do as in the previous days. We start a discussion session with questions for Pedro, and then we take questions for everyone. Questions? If there are no specific questions to Pedro now, so we can take questions to everyone, including Pedro. All the talks you heard this week, Orlando's there, Andres here. Reinaldo is probably here, but I don't see him. Yes, sorry. And Fabio, if he's not here, he said he will show up in the afternoon, so we take questions.
What is the mechanism that improves the neutrino magnetic moment, as you said? What is the best mechanism that way? To improve the magnetic moment of the standard neutrino.
Questions?
You consider an open quantum system. So why you consider that the energy will be preserved? Why you consider the energy conservation in an open quantum system?
It is or to Farenaldos or Pedro. They both can answer. Pedro said about the hiding interactions about in between neutrinos, and in the in the morning, I don't know if I understand well, but you say that when we have two particles, dark matter particles, you can rise the amount of dark matter in the universe, and it's possible using only standard neutrinos to explain the amount of dark matter in the universe using this mechanism of hiding interactions. And yes, trying to explain the abundance of dark matter in the universe using the neutrinos that we know. Then is through this process, no. The you said about the hiding interactions. Yes, yes. Understood. I understand. There's this. Oh, I understand.
I can replace that. So this diagram he drew. Just a second. So I couldn't. So as Pedro pointed out, so the same diagram here contributes to the mu magnetic moment. So you can have this W, and you have neutrino, mu and back. There are some models where you can replace this W by an UW and this neutrino by the heavy N, the capital N I was talking today. Mm-hmm. So this N could potentially be a dark matter particle, the same N that I was talking today. So you can correlate neutrino masses, because this guy will be sort of responsible for neutrino masses. You can correlate mu magnetic moment and dark matter in one model.
I understand.
It's one model.
Thank you. Thank you.
Next question. Sorry. Okay.
I have one too, Andre. This morning you showed that plot with all the scales and all the particles, and it's more a discussion than I don't even know if I will be able to ask a question, but you were talking about particles that we see, and we see that particles and their masses. In the same plot you put the neutrinos 1, 2, and 3 that we actually don't see it, right? Because we see always on the standard model, when we do the Lagrangian, we put the neutrino with their flavors, not the eigenstate of the mass. So I was wondering if makes sense the comparison you made, because all the particles the masses are higher, but they are their own masses, and the 1, 2, or 3, they are not something we are observing. I was just.
So that's a good question. And I think it's always important to, I think, you know, we've all said it maybe a few times, but it's very confusing and it's very important. All the information that we have access to indicates that there are 3 neutrinos, and at least 2 of them have mass. None of these neutrinos are these things that we call the electron neutrino, the muon neutrino, and the tau neutrino. The electron neutrino, muon neutrino, and tau neutrinos are a shorthand version of describing weak interactions. They don't exist. So, you know, so if you learn anything, you should go back home and say, electron neutrinos are not particles. They are just a shorthand notation for describing the object that's produced in a charge current weak interactions. And again, I think I said this at one point to somebody who was asking me a question, but it's very useful to think about this mixing phenomenon in lots of different ways. And one thing, let me just draw something very quickly to remind you of how mixing works in the quark sector. In the quark sector, when you learn about mixing, 9 out of 10 times, you learn about mixing by asking what are the couplings of the W bosons to quarks. Okay, so let me remind you of what you probably learned. And you probably learned that the W boson decays into an up quark and a down quark. So this is the coupling of the W boson to an up and a down. The W boson, of course, can also couple to an up quark and a strange quark. And that's also allowed. And then, of course, you also learn, and let me not draw it again. You know, so there's a W boson coupling to a down quark, W boson coupling to an S quark, and a W boson coupling to a B quark, all of it associated with the U quark. So, assuming that this is very familiar to everybody, you then learn what the Kabibo-Kobayashi-Maskawa matrix is, and it's this coupling right here. Okay? So this is the coupling here, and this is, you know, VUD or VUS or VUB. And these are elements of this mixing matrix, but we describe them as these couplings. The neutrino sector is exactly the same, except that we describe everything using a very different language, and that leads to confusions. But one thing is the W coupling to the electron should also be thought of as very, very similarly that the W couples to the electron and the neutrino number 1, or to the electron and the neutrino number 2, or to the electron and the neutrino number 3. And this coupling here is proportional to the elements of the mixing matrix. Okay? This is almost all the information that you need to know. And at no point I said the thing called the electron neutrino. There's no electron neutrino. However, there's an extra complication in the case of neutrinos that says that if you have a physics process that involves a W boson and the electron neutrino, and you ask for a generic physics process that we talk about which is the neutrino that got produced, the answer is, in quotes, all of them. It's a linear superposition of them. And that's why you see neutrino oscillations. So the distinction, or the biggest difference between the quarks and the neutrino sector, is that these neutrinos have a very, very tiny mass in such a way that you can have a coherent superposition of neutrino states, and you never get to do that with the quarks. Okay? So that's why it's convenient to define this object, which is the electron neutrino, which is this thing here, because it is often the case, and when I say often, I mean all the time, that the description of this neutrino is a coherent superposition of mass eigenstates. And in such a way that you don't have to write this down every time, you give it a name, and you call that the electron neutrino. Now, I will also mention that depending on how you learn particle physics, you probably learned that in the quark sector, you can do the same thing too. There is a name for this electron neutrino in the quark sector, and it's called the D prime. So there's this thing called the D prime, which is a linear superposition of the D, the S, and the B. So it goes like a V, U, Q, Q, and this is a sum over Q equals D, S, and B. So there is this object here, which is the thing that couples the up quark to a W boson, and some people call it a D prime. There's also an S prime and a B prime. And this is not a particle, it's a linear superposition of particles. And when I say particle, I mean some object that has a well-defined mass, so you can define a one particle state for it. So the D prime is not a particle, but it's a combination of well-defined particles that have a well-defined mass, just like the electron neutrino. So the electron neutrino is as much a particle as the D prime is. And given that none of you have ever heard about a D prime, it's probably not something very fundamental. The same is true for the electron neutrino. It's just that the parameters are such that the practical behavior of these things is just completely different. But the fundamental basic physics is exactly the same. So again, that's why it's pretty standard, or there's nothing too unusual about asking what are the masses of these things here, which is a well-defined question, and how does it compare with the masses of these things here, because they are all the things that we call the fundamental particles in particle physics. So that's the very, very, very long answer. But this is very important because I understand it's also very confusing. And our community, if you want, our community, I mean, the particle physics field as a whole is still learning how to properly describe this neutrino oscillations without confusing people too much. And the problem is the language that we had before tends to be the language that we keep using anyway, even when things change, because we're very lazy. We don't like to learn stuff. So we keep calling things the same names that they had before, even as things morph, which is why every once in a while we end up with these things that have these really weird names that make no sense at all. Because again, things change very slowly. But again, so that's one good thing to keep in mind, I think.
And it leads me to a second question. We have a lot of evidence that we have to include something beyond the standard model. But on the standard model, we have this superposition that is electron neutrino, the mu, that is massless. There is some framework that we can describe like this linear superposition in any way on the Lagrangian. It's a massless particle, just out of curiosity.
So that's so again, going back to this long answer, you are allowed to write down the standard model Lagrangian using only the mass eigenstates, and that's often what we do. Now, what you're saying is, let's say that you would like to write down a standard model Lagrangian without neutrino masses, which is what you do, and what happens is when all the neutrino masses are 0, then all of this mixing stuff is completely unphysical. So in that case, you can pick all of these charge current interactions to be flavor diagonal. I can say that the electron neutrino couples to a very specific neutrino, and the muon neutrino couples to another very specific neutrino, and so on. So when the masses are zero, or by the way, if the masses were exactly the same, the mixing doesn't exist. There are lots of ways of saying that the mixing doesn't exist. Another way of saying it doesn't exist is that it can be whatever you want. So you might as well pick the easiest thing, because the answer doesn't depend on what the mixing is. So you pick, and I say this in lots of quotes, you pick the nu 1 to be the electron neutrino, the nu 2 to be the muon neutrino, and the nu 3 to be the tau neutrino, because if the masses are all zero, you can make whatever choice you like, and the answer is always the same. So that's the old picture we have. In that picture, the electron neutrino is a particle with zero mass, and the muon neutrino is a different particle with zero mass, and the tau neutrino is yet a different particle with zero mass. Once you start writing down anything in your Lagrangian where the neutrino will eventually get a mass, then it will become very clear what are the states with a well-defined mass. That may not be in the Lagrangian, by the way, because we tend to write down Lagrangians in ways that look pretty, but are not, but the mass eigenstates are not explicit. But we can always work hard to make everything such that all of the fields that I have written down are proper mass eigenstates. This is something that you probably see when you talk about, well, the Higgs boson is a bad example because it diagonalizes in the same basis as the masses, but there are other examples of when the mass eigenstates are not explicit in your Lagrangian, and you have to work a little bit harder to get them to show up.
To stress one more difference between the quarks and the neutrinos is that the quarks has also the strong interactions. And then it becomes more clear that you should, the UDSB without the prime has some meaning on the strong interactions.
No, it's only some comment, because also you can think why if you want to automate it, compute this rate. Okay, you have some process this. If you compute uncoherent or coherent, because this is something also confuses people. Maybe you can say something about this.
I guess Holanda is asking about, a different question you can ask is, can I use this particular language to describe any physics process? The answer is yes. And I'll let you think about that. You have to do it carefully. I think that's the key point, is again, you can talk about, let's say you wanted to use this language here to describe neutrino scattering on something. So you want to look at this diagram from the perspective of the neutrino coming in and producing an electron. But you would like to say that I have some linear superposition of 1, 2, and 3 that's hitting my target and creating an electron. So can I use these couplings there to calculate that scattering rate? And the answer is yes. And in particular, one thing you can do is you can have a muon neutrino. So I can have a muon neutrino, which again, remember, doesn't exist. But it is a linear superposition of things that exist. So one question you can ask is, if I have a muon neutrino coming in, and it's made out of 1, 2, and 3, and I know how 1, 2, and 3 interact, so I can calculate the muon neutrino coming in, and I can ask, what's the probability that you produce an electron? And remember, the nu 1 knows how to produce electrons, the nu 2 knows how to produce electrons, and the nu 3 knows how to produce electrons. But we know already that this linear superposition of nu 1, 2, and 3 does not know how to produce muon, how to produce electrons. So there has to be a cancellation. And you'll see where the cancellation will be, because the coupling here is proportional to UEI, and the composition of your neutrino here is proportional to U mu I. So if you do the calculation correctly, you're going to get something that's proportional to U mu I, UEI. There's going to be a star somewhere, so just trust me. And this is summed over I. So one of these contributions is from the neutrino number 1 part, the other one is from the neutrino number 2, and the other one is from the neutrino number 3. And that means, if you have this linear superposition of muon of this linear superposition of mass eigenstates scattering off an electron, the probability that scattering off of something and producing an electron, the probability that the electron gets produced is proportional to this number, and this number is 0. And the reason we know that is because this is one of the properties of the unitary matrix. So again, as Holanda was asking, you can do everything in this language, or you can use this shorthand language to remember that the muon neutrino doesn't know how to produce electrons, so the answer is 0. But you get 0 whatever language you choose to use, and you don't ever have to use these fictitious particles as an intermediate state, but clearly it is very useful. So we're not going to give up on it, let's say. But we just have to remember that we understand everything that we're doing.
More questions?